All right, so this is week 4, human factors and HPI tools continued. Last week we left off on function analysis and allocation, so we'll be going back into here. So remember, functional requirement analysis is you decide what needs to be done. Function allocation is we decide who is going to be doing it between a machine or humans. So functional requirement analysis, this comes from EPRI, but the principles are generally the same regardless of your source, source of truth there. So we identify those functions that must be performed to satisfy the plant's operational goals and objectives. These may overlap with PRA and HRA. Remember, those are two completely separate disciplines we're not going to worry about too much. It's not necessarily synonymous with important human actions. So some examples are you need to determine the objectives, performance requirements, and constraints of the design, and with considerations for speed, accuracy, and reliability. So if your system has a built-in timetable before something bad will happen, you need to be aware of that. Define the activities that must be accomplished to meet the objectives. And define relationships between functions and plant processes responsible for performing the function. So as we move into function allocation, one brief kind of tangent is you may run across throughout other classes or just experience, you might hear of levels of automation. If you hear that tossed around, they're referring to Sheridan's 10 levels of automation. And if this is a topic of interest, we can add this to the end of the semester if there's time. But essentially what you need to know is for Sheridan's 10 levels of automation, as you climb through the 10 levels, they necessarily, so there's an increase in automation, which is necessarily linked with a decrease in human action. And that kind of binary situation has kind of been fallen out of favor because it's not super accurate for how complex socio-technical systems function. So it's just important to note it was really prominent for a while, but isn't so much anymore. So, and viewing it as gospel isn't super appropriate, really. Anyway, so the first question, is automation essential? So this is basically the question of, is this action something a human cannot or should not do? So is actual performance of the function a health or safety concern? Does it have to be performed quicker than a human can do it? Does it require a precision greater than a human can do it? Or greater human reliability? We also tend to automate if the specific function has high error rates and high consequences for potential errors. Now, question 2, is automation desirable? So we consider, is the function complex and easier for computers to perform? The function requires many repetitive actions that may be fatiguing or boring to operators. We talked a little bit before about vigilance and how it's one of the most difficult things your brain can do. The function creates high cognitive workload. Remember, high cognitive workload will accompany higher error rates. It creates long periods of boredom. This is kind of similar to the second one, right? Vigilance is still the problem. High physical workload or fatigue. This is specifically something we consider with industrial and some of the more labor-intensive jobs. Or if the function interferes with performance of another function that has to be manually performed. So automate if while humans perform these tasks, or if while humans may perform these tasks, they do not do them well and may be error prone, even if they are not of serious consequence. Then the third question, is human involvement essential? So the function is a core human responsibility, like communication. Automatic responses is difficult, so challenging to model and control logics. The personnel must remain in the loop. we think need to take over control, need to have human involvement, or deliberate tasks to maintain operator vigilance or situation awareness. Also consider, right, with many systems, there is the consideration of, you know, kind of human, I guess what would we call it? Human accountability, maybe, right? That, you know, some critical systems we want a human to be involved. That way there's accountability. You know, if something goes wrong, we can dig in and figure out why and you know, adjust that. Sometimes there's punitive questions, right? That's another aspect that can come into play. So as we use function allocation, so it directly informs design. So the type of control and information automation drives the type of technologies you're going to use for control systems, your staffing levels, any information requirements or visualizations, your procedures and alarm systems have to interact with it. Information from function allocation will also serve as an input to ConOps. So concept of operations, this is something you may have heard of before. What ConOps basically is when these systems or processes are designed, there are like fundamental assumptions about how it is done. And you know, if we think function allocation, right, if we assign tasks to automation or to humans or whatever, that will fundamentally change the nature of the operations of that plant. So, or process, system, whatever. And so we need to look at the high level functions first, but the detailed functions will emerge as INC are finalized. And just a note, a lot of this stuff is going to refer to plants or systems, and it's going to seem very industrial, but literally every system has something like this. You know, I mean, if we think about starting your car, there are functional requirements analysis that could be done on that task, in the sense of you have to have your keys, maybe you if you still have a standard, you know, regular ignition that requires manually turning the key, you know, you have to have those there. If you have a key fob, you know, push button type situation, then the keys will have to be close by. But when we consider function allocation, right, we don't require the human to, you know, manually fire spark plugs at a certain interval. That's an automated function. So, you know, all of these things, and that's kind of the point, right? Is all of these things are incredibly important in spaces like nuclear, where I work, but we do this stuff all the time already. And we interact with systems that this was considered in our just daily life. So just kind of keep that in mind and don't get too caught up with that stuff. Okay, so we're going to take kind of a quick detour down HSI design and user experience stuff. If this really seems interesting to you, again, we can dig deeper later. There's also a human-computer interaction course done in the psych department. So, but this is important, especially in a digital world. You know, if you go back to 1915, HSI design or user experience wasn't really an important component. But for us, in modern times where nearly everything's digital, it is. So we can consider this kind of just a brief crash course in HSI design and kind of some of the considerations. All right, so the one thing that I will say, the broader human factors and any other engineering, psychology, or computer science, or any of these disciplines that adopt some of these things, the one thing I'll say is they're really good at making additional acronyms we don't need. So, you know, a little bit of definitional clarity. So you will hear HCI, HSI, or HMI. Those are the three most common ones. So HCI, human-computer interaction, how humans interact with computers. HSI, human system interaction, and HMI, human machine interaction. Now, the problem in my mind, one of my axes to grind, is that they all seem kind of redundant or collapsible into each other. We can just pick one. Because if we think about it, how humans interact with machines? Typically by computers. Or how do they interact with system? Typically by computers. How do we interact with computers? By using our cognitive systems and specific, aspects of our cognition. And it's, what if everything is a computer system and machine? Um, we'll probably use HSI. It's kind of the middle of the road, but these terms, in my opinion, can be used interchangeably in most instances. But just be aware if you'll hear people will tend to pick their favorites. And this is continuing even beyond these acronyms. There's also a ton of other ones that come up and are kind of redundant. So, but human-centered design also is one of those broader umbrella terms that I wish everybody would just use. So, first step, design inheritance. So, if you are this concept is any system that we use in a digital sense is inheriting user expectations from every other digital system that exists, even if it's unintentional. And this might seem kind of weird, but think about this. If you went to a website and it didn't have a standard menu bar at the top with an about section or services if it's a business or whatever, you would be confused. Why? Because we tend to think that's where things go. That's why some people have a really struggle switching from Windows to Apple or vice versa, because we're used to start buttons or we're used to those kind of things. So design inheritance is a huge thing we have to be aware of when we're considering HSI design. Now, ubiquitous computing is another kind of term that basically means computing is everywhere. We're far away from the times where you used a computer to do very specific math tasks typically, or very basic word processing, but otherwise that was about it. Now we use computers for literally everything, and all devices in some way have a computational aspect. So, and this I pulled these slides directly from one of my nuclear courses. So what does this mean for nuclear, but also what does this mean for every other thing and every other system? So your system needs to align with user expectations that are now defined by everywhere. You have a larger design space for novel digital systems, potential increase in risk, and higher learnability. And this is a quote from a nuclear regulation, but it's HSA modifications should be designed as far as possible to be consistent with users' existing strategies for gathering and processing information and executing tasks. This says identified in the task analysis, but there are some of those we just kind of know, right? There are aspects to a lot of things, though, that are kind of standardized over time, it doesn't matter what brand of drill I grab. Every, battery operated drill will work the same. There's not a ton of differences between them. Cars have similarities, there's a lot of those, and processes are similar. Imagine if you're flying and you go to an airport, right? Your interactions, the overall process you're going to perform to eventually get on your plane is similar whether you're flying with Delta or American Airlines or whatever. We tend to gravitate to systematizing things across the board. So, okay, so these are some other kind of terms, but you'll hear when we talk about design. So you'll hear user experience. This is extremely common in commercial design spaces or software development. It's predominantly talking about user satisfaction. From regulation side, or for our case, safety side, satisfaction isn't super important. We don't really care if people like what they're doing as long as they do it right. But what's important to know is research has shown that if people like using the system, their overall performance increases. So if you want them to do it, again, right, then they should just enjoy it and they will do it right more often. Our kind of metrics or tools for that are user research surveys, predominantly qualitative feedback, and task success. The next one's usability. So this is way more important when we think about regulatory or safety spaces, right? It's the basic functionality and efficiency of the system, so how usable it is. This isn't do we like it or not, it's can we use it. We tend to measure this by time to completion. We'll also do error counts, abandonment, or pathing accuracy. And again, we won't go into a lot of these in depth. That's a HCI course, or we can talk about it kind of over the course of the at the end if we need to. Information architecture. So this is one you won't hear about as much, which is kind of unfortunate because it's incredibly important, but it's quite a bit more foundational. So this is how information is structured and discoverable in your system. This is hierarchies of information, menus, and logical arrangements. So this is in the sense of, right, if we go back to our website example, if I go to the About Us page, if I click that and I get a Contact Us box, I will be confused because that doesn't make sense. Or if I'm in a, we've all kind of probably had this experience where you're using a new piece of software, a new application. I know this especially will come up in like video games, right, where you're trying to find a particular piece of information and you're not totally clear where it is. That's an information architecture problem. We have a natural tendency to seek out information and chunk it in different ways. So successful information architectures mimic that as close as possible. We'll find them, but also measure them by false landings, false starts, time to completion, error counts, and number of clicks. Then lastly, user interface. Sometimes people will use UI or UX interchangeably. Sometimes you'll see job postings that say UI/UX designer, developer, whatever, which is nonsense. They're completely different jobs. So user interface is predominantly a visual medium. We're talking about the design of graphical elements within the HSI and the pictorial means of communication within a system. So this is the shape, color, everything of buttons, icons, text. All of that are UI features, and they're just because they're more graphical or focused does not mean they're at all less important. User interface is really critical. If we go back, recall that so much of our processing is visual. So a good UI is in some cases worth 1,000 UX points. It's really important to think about that. And we capture those. So UI is fundamentally subjective. It's an artistic kind of thing, but we look at it with qualitative reviews, click back counts. So if somebody clicks something and it's incorrect, so they go back. Multiple clicks per element, false starts and false landings. Okay, so the Hicks-Hyman law. So the more choices the user has increases the cognitive response time in a logarithmic fashion. Oh, look at that. It reformatted it and blocked it all. Anyway, it's a big consideration in critical systems where you're going to have a lot of features or a lot of menu options. And it's important to note, since it's logarithmic, right, if you have a system where you just are going to have a lot of options as a function of safety or whatever, then you just have to expect a longer response time. So you will place yourself kind of up here in this curve, maybe. So then you just kind of design your system such that this is your response time, and you don't expect people to live down here. And that's kind of the way the Hicks-Hyman law works, but it's something to just be aware of. And one thing to know is as a general rule, human performance tends to follow logarithmic curves. We tend to hit a top out, and it's not like we then shut down and, we're not computers, we don't get a blue screen of death, but our we'll get to a point of like diminishing returns where our processing will slow. Like here, for example, you see another logarithmic curve. So Fitts law, this is from Paul Fitts, that was his name. The time it takes to navigate to an element is a function of the distance from the cursor and the width of the element. Now, this is one thing to think about that you've probably never thought about before. Why is the start button in the corner of the screen, or the close button in most systems? Well, that's because corners are infinitely wide, according to Fitts' law, because they cannot be missed. And so you should put key actions in a corner. And that's true. Imagine if you close your eyes and you have your mouse, and let's say I want to click on Fitts' law or circle it, and I'm going to try to do that with my eyes closed. If I'm up here, oh, I totally missed. But if I need to I can close my eyes and hit the corner of my screen, no problem. So that's just an interesting thing I like to bring up to people. It's like, hey, that's why stuff lives in the corners. Direct manipulation. Okay, so this is pretty common for any of us that were raised with modern graphical user interface computers. If you have an experience back in the DOS realm or the Windows 3.1 space, it's you'll remember the before times. But otherwise, direct manipulation is the sense of we at least have the perception that we are directly manipulating objects in a digital space. So this all started with Windows 95 and the graphical user interface. We were hacking the physical world into the digital. So think about it. Does your computer have an actual folder? No, not a physical one, not one that looks like these folders. Desktops, drag and drop, those kind of things that are we just think about as aspects of a computer, but those were ways to conceptualize actual functions that your computer's doing. So when you drag a folder from one file, from one or part of your file explorer, from your desktop, let's say, to your documents, you're not actually dragging it. You're telling your computer to execute a move command on the back end. And there was once upon a time where you would have had to type out that move command. But this is one of the ways that they got computers to become more usable for people. Direct manipulation has become a fundamental aspect of all digital design. It's a key expectation. So it's a simple way for us to leverage learned behaviors and increase success on task. But if you don't use direct manipulation, you're going to have problems. Like if it seems to users like they should be able to grab something and move it, you either need to redesign it so they don't think that, if that's a problem, or you need to give them that capability, because it is so fundamental. Consider it like the reality of opening a door and like what a doorknob is. Like direct manipulation has basically become that in a digital sense. So skeuomorphic versus flat design. Again, depending on your age, you may not totally recall skeuomorphic design. It was real popular in the kind of, 2000s, 2010s. So skeuomorphic is we are mimicking physical space. So we lean on existing physical mental models and association. However, it increases the base cognitive load. So examples of skeuomorphic design are the bottom left two here. We have the original Kindle Fire interface here. So this was supposed to look like books on a shelf. There is shadows and aspects there because then users will understand them as distinct elements or components in a touch sense. Similarly, the old school Apple iPhone setup was like this. But if you notice, these are kind of thumbnails, but they're not totally flat. They have, some shading along the corners here and aspects that gives you depth. Notice how you have a reflection aspect down here. That's to, again, give you an assumption of physicality to it so that it's tactile. We're mimicking our tactile perception. And it increases your base cognitive load just simply because there's more stuff to look at. When you have shadows, shading, different weights and depths, then that's, an aspect of that. Well, then we move to flat design. So we have the, again, original Windows 8 screens and the more modern iPhone or iOS approach. So it's cleaner, but it relies on digital mental models and associations. So you have decreased cognitive base load because the visual system isn't perceiving as much stuff, but the associations are not going to be as strong. So that's a trade-off. User research and evaluation will inform which one is best. There is no obvious winner. Okay, so Gestalt principles. So this is, again, I'm giving you some of these things because, like I said in one of the first lectures, you will start to see these problems everywhere. And part of that is because of Gestalt principles. So it was kind of born, it's an early 1900s school of thought from Germany. It means pattern or configuration. And it's essentially are characteristics of human visual processing that can have design implications. So we'll go through this. Both these are the same. They're just two different aspects of it, right? Or two different representations. So proximity, if things are close together, we think of them as separate groups. So like here, your visual system would have perceived this as one group, this is one, this is one. Similarity, we will tend to group, even if they're not next to each other, like proximity, we'll group like items. Closure, so as the human brain ignores gaps and tries to understand the bigger context, so we don't need complete enclosure of a symbol. But also, if we go over here to this version, enclosure also is a grouping mechanism. If we put a border around a set of elements in a system, they again will be inferred by your visual system to be grouped together. Symmetry, that's one big one that we will be able to tell immediately. If you've looked at a website that maybe the CSS went kind of squirrely on it, and so something's just slightly askew, you'll be able to see it really fast. And then, which can be there's design reasons for that. You may not want them to be able to see that, or you might want it to. You might intentionally put something askew so that it draws visual attention. Continuity, elements that are ordered in a line or a curve seem to be in a group if they are following the same curve. And figure and ground is another big one. So the human brain instinctively recognizes if something is in the fore or background, and it is variable, like the optical illusion I put in the Slack at the beginning of the class, right? It is variable what's the fore and the background there, but it's something we can use to design. Next, Nielsen's usability heuristics. So these are other things that we will use for design. We will also use them as evaluation measures. And again, we're not going to go into these super in depth, but if you're interested, you can pause the video and go Google Nielsen's heuristics. There's a million videos on them, or you could read the original papers by Jakob Nielsen, whatever you want to do. But it's essentially, these are expectations of your users, or your expectations your users will have of your system. So visibility is system status. They need to be able to understand if the system is active or selected. Match between the system and the real world. So when I do something in the system, does the real world respond? user control and freedom. This is when we think about undo functions kind of live there. Consistency and standards, right? Your design shouldn't be super inconsistent without a good reason. Error prevention. So again, design for likely errors and give good error messages, which, that's a big one. We've all experienced bad error messages. Recognition over recall. So this is one of my favorite signs, right? Left is such a fundamental concept for us, but between these two signs, this one's actually better, because when you say turn left and that's all you say, you don't have this arrow, you are expecting your users to remember what left is. Now that's a reasonable assumption, but again, to improve performance, you can just put the arrow. Notice these signs are the same size. You can just put the arrow there, and that they can just follow. It tends to be more effective. Flexibility and efficiency of use is important. You don't want your users to feel railroaded into a task if they don't have to be. Aesthetic and minimalistic design, again, this is kind of subjective, but it's based off of the notion that anything that isn't minimalistic is going to increase your cognitive load. Again, help users with errors, and have good help and documentation. And then some other things, OpEx reviews or operating experience reviews. This is another tool we'll use in design. So these are structured interviews with operators or workers to capture the context of the work. Important human actions, we've already talked about those. Verification and validation. So this is in particular a relevant thing for nuclear or critical aspects, but it's something to think about. Is we have to both verify something works and validate that it works, and those are two different aspects, especially when we're talking about a super complex or critical system. And it's essentially just different levels of rigor, right? An application to select your favorite ice cream color or ice cream flavor isn't something that needs a high degree of verification and validation, versus a system for a surgical robot probably should have a high level of verification and validation. So just different levels there. So now we'll do a brief talk about HPI tools, and we'll probably go into it a little bit again next week, but the thing with HPI tools, like I said, they're all post hoc. So, we've kind of, I think by this point, right, you should have enough about the human factors kind of baseline of design to understand, okay, that's how we get human errors to occur as infrequently as possible. But they're still going to happen. So how do we add additional behavioral controls to make them happen even a little bit less, but then also to kind of untangle what happened? And so behavior changes are where HPI lives. We're talking about self-check, peer check. So this is, checking yourself before you do something. Peer check is, if you're working with a partner on a team, you always have somebody, verify what you're doing. Walk downs, this is something you might have heard about. This is where you have a work task in an area or maybe on a particular piece of equipment, and long before you actually do the work, you're going to go and actually walk around the space, the physical space, see where you're working, what you're doing, etc., so that you can kind of, again, start to build that mental model in an accurate way, be aware of any risks and those things. You'll also hear stop when unsure. So that's the idea that you can stop if you think you're doing something wrong or something seems fishy. Just culture is another term you'll hear tossed around. Just culture was, I think it was from the 90s. It was a Boeing executive that I cannot ever recall his name, kind of, I think, was the first to come up with that term, but I mean, it's not a novel concept. And then Sidney Dekker wrote the book Just Culture, but it's essentially about removing a sense of retaliation and blame from your organization, so that if somebody sees something that's wrong, they can bring it up without any retaliation or punitive effects. And vice versa, if they do make a mistake, it's viewed as a learning experience versus an opportunity for blame. And lastly, the most important part, right? The vast majority of industries don't do any of this. And especially not, even if they do it in some way, they don't do it in a structured sense at all or consistent. So HPI is kind of a unique thing in some spaces. Some people would say, oh, yeah, all of these things are common sense. You'll hear that, right? Or like just culture. Well, yeah, that's just a good management philosophy and things. Okay, well, a lot of places don't do that. So um, it's important to kind of keep that in context. Okay, so next, like I said, we'll talk about HPI tools a tiny bit more, but we're really going to be going into investigations next. The role of an HPI investigation, how you find root causes, the different tools, how do we evaluate human performance, so pre and post event differences. And what's interesting, right, is once something happens, then it happens. It exists forever. It becomes fixed reality. But our perception of it is completely malleable and flexible. And there are pros and cons to that. So we'll go into some of these aspects. All right, thanks.